All right, we're going to do activity 312 now for differential equations. This continues our lecture where we're basically, like I said, it's like if linear algebra and differential equations are people, then differential equations, I'm not sure if they're stealing, maybe it's just borrowing. So differential equations is just like walking into linear algebra's garage and grabbing all those tools and walking back over to his house without telling anyone. He didn't work with those tools. He didn't figure out how those tools work. Just like, hey, I need these. So the next thing for, hey, I need this is eigenvalues and eigenvectors. Okay, in linear algebra, we spend a lot of time trying to figure out what these things actually mean, trying to get our heads around them, trying to understand them. And in this case, all we need to do is compute them and use them. Okay, so say you've got A equals 1, 3, 1, negative 1. I want to find the eigenvalues of A. So what I do is depends on if you like lambda or x. Traditionally, we use lambda for eigenvalues. So to find the eigenvalues, I'm going to do the determinant of the matrix 1 minus lambda, and 3 stays the same, and 1 stays the same, and negative 1 minus lambda. Okay, well, determinant is the diagonals this way minus the diagonals that way. So that's equal to, so the determinant is when the lambda's in this equation is equal to 0. So then that diagonal, 1 minus lambda, times that diagonal, negative 1 minus lambda, and then minus the other diagonal, minus 3 equals 0. So I need to do some foiling. By the way, this right here is called the characteristic polynomial of the matrix. They make sure to define that in this section. It has there's a lot of things that go behind that name and what it's all about. But that's all you need to know is like how to find this determinant. So how to find these eigenvalues. So here we've got that. And so then we got to do some foiling here. So first, outside, inside, last, 3, 0. So that means those cancel out. We got lambda squared minus 1 minus 3, so lambda squared minus 4 equals 0. Okay. Now, most of the time, you end up with a lambda here term too. So you either have to factor or use the quadratic formula. This one, I could just add the 4 over and take square root of both sides, but I'll factor anyway. So factoring gives me lambda minus 2 times lambda plus 2 equals 0. So then if these two things multiply together get 0, one of them must be 0. So lambda equals either 2 or negative 2. Okay. All right, now I got to find an eigenvector for each eigenvalue. All right, so here, to find the so this is eigenvalues. Eigenvalue is a value, it's a number. Eigenvectors are vectors. Okay. And then, by the way, something we talked about in linear algebra that was just kind of fun, that was the first time I'd heard it, was that the name eigen comes from like the way that sound reverberates in a room, so in music. So there's certain spots where in a room where a room of certain length playing a certain instrument, you get certain nice reverberation. So that you call those like eigenspaces. And so that's basically, mathematicians took that idea from like music theory and music halls and then used it for linear algebra here. So eigenvalues are these values that the matrix does this nice thing with vectors. And so now we got to find the nice vectors to work with the nice values. So what I need is 1, 3, 1, negative 1 times some vector equals 2 times that vector. And then I also need to do it for the other eigenvalue. 1, 1, 3, negative 1 times xy equals negative 2 times xy. So this will be the eigenvector for the positive 2. This will be the eigenvector for the negative 2. Okay. So now that means that this is not quite the fastest way we could do it. If I'm only teaching you technique, I might as well teach you fastest way. All right. So the faster way is that, you know how we did that minus lambda up here? Take this matrix with the minus lambdas and plug in the lambdas. So here, 1 minus 2 is negative 1, 3, 1, and then negative 1 minus lambda is negative 3 times xy. This time equals 0, 0. Okay? So like I said, this is just computationally. So what's interesting about eigenvalues, eigenvectors, is that this will be the vector that the matrix times that vector is the same as 2 times that vector. Okay? That's pretty interesting, but finding it is better to plug in those lambdas and then solve this equation. It's just because you've got less x's. All right, so then this means we're looking for negative row times column plus 3y, and the other one is x minus 3y equals 0, 0. Now you should notice that these are basically the same equation then, so you only need to really solve one of them because it's like the same equation repeated. So then solve for x or solve for y. So in this case, so 3y equals x. So that means I can substitute where I have x as like a 3y. So then my vector then would be 3y, y. And so, sorry, I can't see. So from here, I get the 3y equals x. And so then this is my vector. Instead of xy, I can substitute the 3y for the x. Now I just need one of these vectors. This is an infinite number of vectors because y could be anything. I just need one of them. So pick your favorite y that's not 0. Okay? My favorite y most of the time is 1. Although I sometimes make it other numbers if I have fractions to try to get rid of fractions. So eigenvector I'm looking for here is 3, 1. Okay, that's the eigenvector for lambda equals 2. Now let's do it for lambda equals negative 2. So again, instead of doing it this way, do it the fast way. So 1 minus negative 2 is positive 3, and 3, and then 1, and then negative 1 minus negative 2 is really negative 1 plus 2, which is 1. Okay, now just like last time, I basically have the same equation here when you do the matrix multiplication. So row times column, you have 3x plus 3y, and then equals 0, which would be like, well, and then you have x plus y equals 0, because you have this vector equals that vector. So that means just means the top is equal to the top and the bottom is equal to the bottom. So this is basically the same equation, just this bottom one's a little simpler. This should always be the case. If you have a correct eigenvalue, you should get basically the same equation here when you're doing this step. Okay. So then let's just do like x equals negative y. So then my vector, so I can plug in for x, it's negative y, y. And then my favorite value of y is still 1. So my vector would then be negative 1, 1. That's for lambda equals negative 2. So that's how you find the eigenvalues and eigenvectors of a matrix. That completes part A.